Okay, great. Good afternoon, everyone. This is Jianqiang. I'm assistant professor in civil engineering at the University of Massachusetts Lowell. Today, I'm going to work with my doctoral student, Mr. Akapara, to present our updated research on the structure and the properties of alkali-silica reaction gel treated with lithium nitrate. It's well known that the alkali-silica reaction is a reaction between the amorphous silica from the reactive aggregate and the alkalines from cement. So the result of this reaction is the formation of the hygroscopic ASR gel. This ASR gel can absorb moisture and water to have volume swelling inside the concrete. So this can result in the concrete expansion and cracking. So in the presence of cracks, the ingress of external moisture and aggressive source can ingress into the concrete, can result in multiple degradation mechanisms. This is why the ASR is also called concrete cancer. And when we consider the entire chemical reaction and a deterioration process caused by ASR gel, ASR, we found that's the most critical part of the ASR gel. Regarding the ASR gel, challenges still remain in this area. For example, the understanding of the correlation between the ASR gel at mature level and the concrete deterioration at the structural level is still missing. The mechanism of gel formation, moisture uptake, and swelling kinetics is not fully understood. The mechanism of ASR mitigation using lithium admixture is not really understood. And we know that lithium nitrate is one of the most effective admixture that can be used to mitigate ASR, but the effect of lithium nitrate on the structure and properties of ASR gel is still missing. This is why I would like to do this study with the objective of understanding the synthetic ASR gel with wiring compositions in large quantities, which can be used to facilitate the structural and property evaluations at the ASR gel level. We also do the understanding of the role of lithium in modifying the reaction products and the molecular structure of ASR gels, as well as the comprehensive characterizations of freeze falling, moisture absorption, desorption behavior, the developmental strengths, and dynamic mechanical properties. Based on all these results, we also analyze the correlations between gel chemistry and the properties. So before this study, in one of our previous works, we studied the influence of chemistry or chemical compositions of ASR gel on its structural and mechanical property. We studied 3 different calcium to silica ratio and then 2 alkali to silica ratio. From this study, we found there are 2 most representative ASR gels. So one is at the low alkali to silica ratio, and another one is high alkali to silica ratio. For both of these 2 ASR products, we have the calcium to silica ratio 0.3. For low alkali level, the sodium to silica ratio and the potassium to silica ratio is 0.3 and 0 respectively. At the high alkali level, the sodium to silica ratio and potassium to silica ratio was increased to 0.8 and 0.2 respectively. By focusing on these 2 gel products, we studied 3 different lithium to alkali ratio in this study. So from 0.1, 0.3 to 0.5. I'm going to have my doctoral student Mr. Akapara, to show our results.
Hello. So I'm going to go over the results and discussion from this study. So for characterizing the ASR gels for both low alkali and high alkali groups, we used X-ray diffraction to study the phase composition and their development over time. We can see that there is a most significant peak at 29.42 theta, which is representative of a CSH-like structure or one similar to the naturally occurring mineral tobormorite. So from the study, we can see that adding lithium to the low alkali groups really does not have much effect on it, and there is no new phase formation even after 60 days. Most of the products are formed after 7 days, and they kind of remain the same even after 60 days. Whereas in the high alkali groups, we can see that lithium admixtures, when they're having a lithium to alkali molar ratio greater than 0.1, they can delay the formation of the ASR phase. So at 7 days, we can see that there are the peaks from the raw materials, which are portlandite and silica, and there are really no peaks from tobermorite. Over time, the raw materials are consumed and the tobermorite phases show up, but they are very amorphous in nature. And it is worth noting that as the lithium to alkali ratio increases, the amorphousness of the gels increase. So we did Raman spectroscopy on both the low alkali and high alkali groups after 60 days. So we can see that the characteristic ASR phases are around 400 to 800 centimeter inverse Raman shift and between 950 and 1150 centimeter inverse Raman shift. They are mainly due to the silicon-oxygen-silicon linkages and silicon-oxygen stretchings, and they are Q2 and Q3 polymerization sites which are present. Now we know that Q3 polymerization sites are mainly attributing to the swelling and moisture absorption of the ASR gel. By adding the lithium, we can see that the Q3 sites are kind of decreased beyond the lithium to alkali ratio of 0.1. And there is the formation of a new phase due to the nitrate from lithium nitrate. It may be due to the formation of sodium nitrate, which is further verified in thermogravimetric analysis, which I will discuss in the next slides. So we can see here that the high alkali groups show a majority of Q3 phases, which are more than the Q2 phases, and the low alkali groups show more Q2 phases. So this is indicative that the low alkali groups are behaving like a CSH and the high alkali gels are behaving like ASR. So for the infrared spectroscopy, we did Fourier transform infrared spectroscopy using attenuated total reflection method. And in that study, we can see that the results show similar ASR functional groups from the silicon-oxygen-silicon bonds and the silicon to oxygen symmetric stretchings. By the addition of lithium nitrate, we can see that these phases are reduced as the lithium to alkali ratio increases. In the low alkali groups, there is a single significant peak, which is indicative of a CSH-like structure, whereas in the high alkali groups, we have a compound or like multiple peaks in the 950 centimeter inverse area. So as the lithium to alkali ratio increases, we can see that the phases corresponding to the Q3 silicon-oxygen-silicon bending is decreased, and we can see the appearance of or increase of the nitrate group from the lithium nitrate. Also, the loose bound water or the hydroxyl group is indicated by a broad peak from 3,000 to almost 3,700 centimeter inverse wave numbers. And the low alkali groups show a more, like a much lower intensity of the loosely bound water, which agree with our assumption that the high alkali groups have more Q3 polymerization sites and can like incorporate more water in their gel structure. With the addition of lithium nitrate, we can see that there is a slight increase in the loosely bound water, which might be because of the hygroscopic nature of lithium nitrate. We have verified this further in our DVS studies. We did a thermogravimetric analysis by heating from 30 to 900 degrees Celsius at 15 degrees Celsius per minute. And the weight loss shows a compound singular weight loss at 30 to 150 degrees Celsius, which can be due to the free or loosely bound water and CSH. Now, the high alkali or ASR-like groups show additional two peaks between 175 and 250 and 300 to 360 degrees Celsius. As we add the lithium nitrate, we can see the appearance of a new weight, a weight drop in a new temperature range of about 650 to 750 or 800. And that is due to the formation of sodium nitrate, which we kind of guessed previously. Now, upon addition of the lithium nitrate beyond the lithium to alkali ratio of 0.1, we can see that it can eliminate both of the ASR peaks, whereas the lithium to alkali ratio of 0.1 is only capable of removing only one peak due to the ASR. So next, we did the shrinkage and swelling behavior by monitoring the volume change. For the shrinkage behavior, we sealed the gel and we used methodology similar to the methodology for measuring chemical shrinkage in cement pastes. And after the shrinkage became stable, we subjected the gels to a simulated pore solution and also a 99% relative humidity environment. In the simulated pore solution, there was direct interaction between the gel and the ions since they were immersed in a liquid, but the 99% relative humidity was only through absorbance through a permeable tape. The results show that the low alkali groups do not show any expansion, and the high alkali groups show quite significant expansion, both in simulated pore solution and 99% RH. Now, in a pore solution, the expansion is greater, which may be due to the interaction of the ions between the gel and the pore solutions. Now, upon addition of lithium, we can see that the low dose or 0.1 molar ratio of lithium causes a significant increase in swelling as compared to the control group in the pore solution, which is quite surprising and is a new finding that we would like to explore. As the lithium to alkali ratio goes beyond 0.1, however, the swelling is decreased and there is continuous shrinkage. And in the 99% RH, the swelling is decreased for both 0.1 and the ratios beyond 0.1. So going on to the dynamic vapor absorption test, we studied the mass gain or loss by varying the RH from 95 to 0 and then going from 0 to 95 in 10% steps. And the step changes were initiated when the variation of mass, the rate of variation of mass and to time reached 0.0015. So we can see that the low alkali groups show significantly lower capability of absorption of moisture than the high alkali groups. And by addition of lithium, the absorption of moisture is increased, but the swelling is decreased. So because of the hygroscopic nature of lithium, the lithium nitrate, we can see that there is an increase in the mass uptake of water. The isotherms show a similar behavior to the variation of mass curve, and we can see that the slope of the isotherms are lower in the low alkali groups, and they are higher and increasing with the addition of lithium nitrate. Next, we studied the mechanical properties of the ASR gel by testing 1-inch cubes in compressive strength in a universal testing machine at a loading rate of 100 pounds per minute. And we did a dynamic mechanical analysis to test the modulus of elasticity of small disc-shaped specimens of having diameter like 8 millimeters and the thickness of 5 millimeters. We can see that as per our previous findings, the CSH-like gels are the low alkali gels, and they have a significantly higher, almost 5 times the compressive strength of the high alkali or ASR-like gels. And application of lithium is not very significant in changing the compressive strength of the CSH-like gels, but can reduce the compressive strength of the ASR-like gels. The modulus of elasticity tests show that the lithium nitrate admixture is incapable of changing the modulus of elasticity or might slightly increase it for the low alkali gels. And the setting time of the high alkali gels was also increased by the addition of the lithium nitrate. Now, to go to the conclusions, we will just summarize the points. So the behavior of the synthetic gels depend on the alkali to silica ratio, and the low alkali gels display CSH-like properties having low swelling and high mechanical strength and stiffness, while the high alkali or ASR-like gels are showing high swelling and moisture absorption, as well as lower mechanical strength. Now, lithium nitrate can delay the formation of ASR phase in the high alkali gels with lithium to alkali molar ratio exceeding 0.1. And the Raman spectra has shown that the polymerization, Q3 polymerization, which is mainly responsible for the swelling and moisture incorporation, is reduced by the addition of lithium nitrate beyond 0.1 molar ratio. And also the FTIR results have shown that they are capable of reducing the intensity of the ASR-like phases. Sodium nitrate was formed as a byproduct due to the lithium nitrate doping. And although lithium nitrate is hygroscopic in nature and its addition can increase the moisture uptake capability, but the swelling is decreased beyond the lithium to alkali molar ratio of 0.1. The strength and stiffness of the CSH-like gels were unaffected and increased slightly by the addition of lithium nitrate, whereas the ASR gels showed a diminished compressive strength and longer setting time in the presence of lithium. To sum it up, this study is supported by the National Science Foundation, award number 1935799, and the authors would like to express sincere gratitude to lab manager, Mr. Howe at UMass Lowell, for his assistance with the tests. Thank you. If you have any questions, please feel free to ask.
All right, that's very informative presentation. We have time for one quick question, if you have.
Yeah.
It looks like there's no question. Then let me ask you a quick question. Sure. If alkali-silica reactions become active, then is there any way to stop the reactions or to slow down them?
Yeah, so from our studies, we find that like after 7 days that we made the gel, adding the lithium nitrate with the lithium to alkali ratio of more than 0.1, for example, 0.3 and 0.5, does not produce any alkali-silica reaction phases, as can be shown from this figure.
All right, thanks very much.